We have seen in the previous video the definition of the impedance matrix and the admittance matrix for n-port network. Now in this video, we are going to discuss the scattering matrix for n-port network. Effectively, the scattering matrix for any microwave network may be the most important network representation in microwave engineering. Usually, we represent any microwave component or any microwave network in terms of scattering matrix, and if it is required to represent in other forms, we convert from scattering matrix to the other forms. And also, the measurement tools or the most important measurement tool in microwave engineering is the vector network analyzer, which actually is based on measuring the scattering matrix of two-port network. And from this two-port network, we can generalize the problem for n-port network. We start with that a practical problem exists when trying to measure voltage and current in microwave frequencies. So if we are interested in impedance matrix and admittance matrix, it is required to measure the voltage and the current, which is quite complicated in microwave measurements. However, if we are going to measure the incident voltage and reflected voltage, it would be much simpler than the amplitude of the total voltage and the amplitude of the total current. A representation more in accord with direct measurement and with ideas of incident, reflected, and transmitted waves is given by the scattering matrix. The scattering matrix relates the voltage waves of the incident on the ports to the reflected voltage from these ports. So effectively, the scattering matrix is the relation between the reflected voltage and the incident voltage in the different ports of the network. For some components and circuits, the scattering parameters can be calculated by using network analysis, as we will see in, for example, in Chapter 7. There are some components like power dividers and couplers and so on. We can calculate the scattering parameters for these networks. For other components which can not be calculating, or for other components which have scattering matrix cannot be calculated directly, it can be measured. So otherwise, the scattering parameter can be measured directly by using vector network analyzer. And as I mentioned, vector network analyzer is a basic tool in microwave engineering. Vector network analyzer is a tool that can determine the reflection coefficient and the transmission coefficient for a two-port network, and it determines these coefficients in their complex form, so it determines the amplitude and the phase. That's why we are calling a vector, because this vector quantity include both the amplitude and the phase for both the transmission and reflection coefficient. And from the transmission and reflection coefficient, we can obtain the scattering matrix for n-port networks, for any n-port network. So, even it can be calculated or measured. Once the scattering parameter of the network are known, we can convert it to other matrix parameters if it is required. For example, if you are interested in impedance matrix or admittance matrix, by using the scattering matrix, we can calculate the impedance and the scattering matrix. So, scattering matrix is simpler for measurement, and Based on the value of the scattering matrix, we can obtain the other forms of the network matrix. The definition of the scattering matrix, if we have n-port network like this, so the output voltage or the reflected voltage from each port should be V1 minus, V2 minus, V3 minus until Vn minus. So the reflected voltage equals the scattering matrix multiplied by the incident voltage. The incident voltage in this case would be V1 plus, V2 plus, and so on until Vn plus, such that V1 minus equals S11 multiplied by V1 plus S12 multiplied by V2 plus S13 multiplied by V3 plus until we reach S1n multiplied by Vn plus. Similarly, V2 minus equals S21 multiplied by V1 plus S22 multiplied by plus S22 multiplied by V2 plus V23 multiplied by V3 plus until we reach plus S2n multiplied by Vn plus. Symbolically, we can represent the scattering matrix as the vector V minus equals the scattering matrix S multiplied by the vector V plus. The definition of the element of the scattering matrix Sij is the output voltage from port I Vi minus over the input voltage as the port J Vj plus when the input ports in all other ports except the port J are 0. This means that if I'm interested in measuring S12, I'm going to calculate V1 minus from port 1 to V2 plus at port 2, V1 minus at port 1 to V2 plus at port 2, when V plus at all the other ports is 0. What will make the incident voltage at all the other ports to be 0? If I'm going to assume that the other ports are open circuit, then when I'm going to excite from port 2, V2 plus, some of the power is going to port 1, some of the power is going to port 3, some of the power is going to port 4, and so on. So we have V1 minus, V3 minus, V4 minus, and Vn minus. If this is open circuit, as a transmission line, there will be reflection at the terminal of this transmission line section. And the reflection in this case would be Z load minus Z naught over Z load plus Z naught. And Z load here is infinity. So the reflection coefficient here is unity. So if we have V3 minus and the reflection coefficient is unity, so V3 plus would equal V3 minus. This means that if I have left this port as open circuit and this port as open circuit, all the power that has been transmitted from port 2 to the port 3 would be reflected back from port 3 to the circuit. So in this case, V3 plus will not be 0. V3 plus in this case would be gamma, which is 1 multiplied by V3 minus. So open circuit, does not satisfy the condition that Vk plus equals 0 for k does not equal j. Okay, what will be the situation if I have a short circuit? If I have a short circuit, once again, this is terminated transmission line by short circuit. Z load would be 0. So the reflection coefficient is Z load minus Z naught over Z load plus Z naught. It would be minus 1. This means that if I have incident voltage V2 plus, some of the power will be transmitted to V3 minus and it would be reflected back as V3 plus. In a similar way, the other ports. So if I'm terminating the other ports with short circuit, there will be V3 plus, V4 plus, and Vn plus. So what is the solution? Actually, the solution is that to terminate the other port with matched load. So if this has a characteristic impedance Z3, for example, should be terminated by Z3. If this port has a characteristic impedance Z4, should be terminated by Z4. If all the ports has a characteristic impedance Z0, for example, they should be terminated by Z0. In this case, the power going from port 2 to the network, some of the part is going to port 3, and if I have Z load equals Z0 here, so the reflection coefficient would be 0, all the power V3 minus will be matched or will be absorbed by the matched load, and there will not be reflected V3 plus. So to make Vk plus equal 0 for k does not equal j, it means that all the other ports should be terminated by a matched load. Each other port should be terminated by a matched load, such that the reflection coefficient from the port would be 0. So any power going from the feeding port to the other ports would be completely absorbed by the matched load. In this case, if I'm interested in S12, I'm going to measure the power going outside port 1, V1 minus, when I'm going to excite port 2 by V2 plus. So V2 minus, V1 minus over V2 plus equals S12 when Vk plus equals 0 for all k does not equal 2 for S12. This means that also the measuring tool for measuring V1 minus should have a characteristic impedance equal Z0 such that it absorbs all the power V1 minus and does not reflect V1 plus. So even the measuring tool should have the same characteristic impedance of Z0. If I'm interested in measuring S22, for example, this would be S2 minus over S2 plus when S or V1, V2 minus over V2 plus when Vk plus equals 0 for other k. Means that all the other ports would be matched, and I'm going to use a source for V2 plus and receive the value of V2 minus by taking the ratio V2 minus over V2 plus. I get S22. Okay, so Sij equal the transmitted voltage from port I, Vi minus, over the incident voltage at the port J, Vj plus, when the incident voltage at the other ports except the port J are 0, and the incident voltage would be 0 at the other ports when the other ports are terminated by Z0, or the characteristic impedance of the transmission line. As an example, assuming that we have this T network composed of two resistances, 8.56 ohms, with a shunt resistance 141.8 ohm, and this port 1 and this port 2, and assuming that Z0 of the ports is 50 ohms, and it is required to determine the scattering matrix of this network. This two-port network, it means that its scattering matrix is 2 by 2. So we have S11, S12, S21, and S22. Okay. To obtain S11, it would be V1 minus over V1 plus when V2 plus equals 0. V2 plus would be 0 when the port 2 is terminated by the characteristic impedance 50 ohm. This means that to make V2 plus equal 0, we have to add shunt resistance here equal 50 ohms. In this case, the input impedance at port 1 equal the impedance 8.56 plus the combination of this impedance. The combination of this impedance is actually 8.56 plus 50 ohms parallel to 141.8 ohm. So this combination is 141.8 multiplied by 58.56 over the summation. This is the input impedance here plus the impedance 8.56. So the total input impedance in this case is 50 ohm. V1 minus over V1 plus at the port 1 correspond to the reflection coefficient at port 1. And the reflection coefficient is actually Z load minus Z naught over Z load plus Z naught. Z load or Z input is 50 ohm and Z naught is 50. So 50 minus 50 over 50 plus 50, this would be 0. This means that S11 would be 0. From the symmetry of the problem, it can be expected that S22 is 0 too. Because to calculate S22, we are going to terminate port 1 by 50 ohm, and we are looking from port 2, the input impedance here would be 50 ohm, and we can obtain the reflection coefficient from port 2, which is V2 minus over V2 plus when port 1 is terminated, to be 0. So S22 is 0 from the symmetry of the problem. Now it is required to determine S21. S21 is given by V2 minus over V1 plus when V2 plus equals 0. V2 plus equals 0, it means that the port 2 is terminated by Z0, and Z0 is 50 ohm. So we have 50 ohm between these two terminals. Okay. Now it is required to determine the output voltage V2 minus to the input voltage V1 plus here. Because S11 and S22 equal 0, This means that V1 minus, when the port 2 is terminated by 50 ohm or by Z0, V1 minus, it would be 0. This means that the total voltage at port 1 when port 2 is matched, in this case, equal V1 plus. So V1, which is actually V1 plus plus V1 minus, and V1 minus here is 0. So V1, it would be equal V1 plus. And because here this is matched load Z0, all the voltage here is coming is V2 minus, because there is no reflection V2 plus, because here we have a matched load. So all the voltage at this point, when this is terminated by Z0, corresponds to V2 minus in the present case, not in general, in the present case. So when this is terminated, the total voltage at this point is V2 minus. Thus, we are going to terminate this by 50 ohm and calculate the voltage at this point with respect to the voltage at this point, and this would correspond to V2 minus over V1 plus, which correspond to S21. Okay, so it is required to obtain the voltage at port 2 when it is terminated by 50 ohm in terms of the voltage V1 at port 1. At the beginning, we are going to calculate the total input impedance. So the total input impedance here is 50 ohm. So the total current I here is V1 over 50. V1 over 50 ohm. This is the total current. This total current is divided in the two branches from here and here. The current in this branch equals the total current, which is V1 over 50, multiplied by the impedance 141.8 ohm over the total impedance or the parallel impedance, this and this. Here V2 minus equal V2 equals V1 multiplied by 41.44. 41.44 is effectively coming from what? From the ratio. This impedance parallel to this impedance. So this is the total impedance here. 41.44 is the total impedance at this point. Over 41.44 plus 8.586 is the total impedance here, which is a 50 ohm. This actually is a 50 ohm. V1 over 50 multiplied by the total impedance seen here. So this is the total voltage at this point. V1 over 50 is the total current multiplied by the total impedance seen at this point. So this is the voltage at this point. The voltage at this point is divided between this resistance and the 50 ohm. So the voltage at this point is the voltage at this point multiplied by 50 over 50 plus 8.56. Once again, we have voltage V1 and the input impedance here is 50 ohm. So the total current coming from this point is V1 over 50 ohm. Actually, this 50 ohm is a combination of this resistance plus the resistance of this combination. The resistance of this combination is 141.8 ohm parallel to 58.56 ohm. So this is the parallel combination. Okay. Now the voltage at this point is the impedance of the parallel combination multiplied by the total current, which is V over 50. So the impedance of this combination is 41.44 ohms. So this is the voltage at this point. Now, this voltage is applied to this branch and is applied also to this branch. We are interested in the first branch. This voltage is divided into the first branch into a component in 50 ohm as 50 the voltage at this node multiplied by 50 over 58.56, which is 50 plus 8.56. So this is the voltage at this point, which is 0.707 V1. This means that V2 minus over V1 plus, which is S21, equals 0.707. In a similar way, we can prove that S12 equals S21 equals 0.707. Actually, this circuit is defined in microwave engineering as an attenuator. The attenuator, which is attenuating the signal, and here we have attenuated the voltage by a ratio 0.707. If we are talking about the power is proportional to the voltage square. So the output voltage in this case is 0.5 the input voltage or the input power at port 1. So if the input power is V1 plus squared over 2Z0, then the output power is V2 minus squared over 2Z0. And from this ratio, we can say that is S21 multiplied by V1 plus squared over 2Z0, which is S21 squared multiplied by V1 squared over 2Z0. This effectively the input power. So this V not squared and S1 squared here is square value of 0.707 is 1 over 2. So this V squared 1 squared over 4 Z0, which is half the input power, or in other words, it is minus 3 dB of the input power. This actually is the circuit of a minus 3 dB attenuator in microwave engineering. Okay. Now, if we are interested to obtain the impedance matrix from the scattering matrix, assume that the characteristic impedance are normalized to be unity, such that the characteristic impedance of all ports is 1. The relation between the voltage and the current at the different ports, Vn at the port N equal the incident voltage Vn plus the reflected voltage Vn minus. The current equals In plus minus In minus. In terms of the amplitude of the voltage, it is 1 over Z naught N multiplied by Vn plus minus Vn minus. And because we are assuming that we have normalized characteristic impedance, the current is obtained as Vn plus minus Vn minus. The relation between the voltage and the current is given by the impedance matrix. The impedance matrix states that V equals Z multiplied by I. But I here, it can be represented as the vector of V plus minus the vector of V minus. So Z multiplied by I equals Z multiplied by V plus minus Z multiplied by V minus, where V plus is the vector of the incident voltage at the inputs and V minus is the reflected voltage at the inputs of the network. And as I said, Z multiplied by I equals V, the impedance matrix multiplied by the vector of the current equals the vector of the voltage. Here the total current, here the total voltage. The total voltage can be represented in terms of the incident and reflected as V plus V minus, where V plus is the vector of the incident voltage and V minus is the vector of the reflected voltage. Now we have relation between V plus and V minus such that if we taken the part related to V minus in this side and the part related to V plus in this side, so this would be Z plus unity matrix multiplied by V minus would equal Z minus unity matrix multiplied by V plus, where the unity matrix is a diagonal matrix of order n of n, n multiplied by n, and all the diagonals is unity. Should be noted here, this is Z V plus minus V minus V plus has been represented as Z minus U V plus. Here plus Z V minus plus V minus has been represented as Z plus U V minus. Now the relation between V minus and V plus is actually V minus equals the scattering matrix S multiplied by V plus. So if we are going to multiply both sides by the inverse of this matrix, so the inverse of this matrix multiplied by this matrix would be unity. This would be V minus. Here it would be the inverse of Z plus U multiplied by Z minus U equals V plus. And V minus is related to V plus by the scattering matrix. So the scattering matrix is, in terms of the impedance matrix, it can be determined as the impedance matrix plus unity matrix, all of them to the power minus 1, or in other words, the inverse of this matrix, multiplied by the matrix Z minus U. If we are talking about one port network, in the case of one port network, we have only Z11, and U in this case it would be 1. So in this case, it would be Z11 minus 1 over Z11 plus 1. And we say that the characteristic impedance is normalized to be 1. So effectively, you are talking about Z load minus Z naught over Z load plus Z naught. And this is the conventional reflection coefficient. So this is the general form for the simple equation of the reflection coefficient, which is Z load minus Z naught over Z load plus Z naught. It is originally, in terms of the impedance matrix, the inverse of the impedance matrix Z plus unity multiplied by the impedance matrix minus unity, and assuming that the impedance or the characteristic impedance is normalized to be unity. Here, how to obtain the scattering matrix from the impedance matrix? What will be the situation if I'm interested in the impedance matrix from the scattering matrix? In this case, we can say that V minus, it can be replaced by S multiplied by V plus. So here, this can be replaced by S multiplied by V plus. So in this case, Z multiplied by S plus U multiplied by S equals Z minus U. Now, if we get the Z in one side and S in the other side, we can say that Z multiplied by S plus U equals Z, sorry, here, uh, Z multiplied by S minus U. Minus Z here, minus Z multiplied by U. So Z multiplied by S minus U would equal minus U multiplied by S. So, okay, let us take this to the other side. So Z multiplied by U minus Z multiplied by S equals U plus U multiplied by S. So U plus S multiplied by U minus S to power minus 1 equals Z. How comes? I'm going to transfer this matrix to this side and transfer this unity matrix to this side. Okay? So here it would be represented as Z multiplied by U minus S. And here will be represented as U plus S. Then I'm going to multiply it from this side by U minus S to power minus 1 and this side by U minus S to power minus 1. This U minus S to power minus 1 multiplied by U minus S in this side to be unity. So the remaining part would be the impedance matrix Z. So Z equals unity matrix plus S multiplied by the inverse of unity matrix minus S. Once again, if I am talking in terms of one port network, I have Z11, it equal 1 plus gamma over 1 minus gamma. So the input impedance in this case 1 plus gamma over 1 minus gamma for the case of one port network. Okay, all right.